Okay, so today we're going to talk about the 8.3, the volumes. I intend to do this section in 4 separate lectures. So this will be the first of those. Okay, so volumes. How do we do volume? So volume as an integral. If you look at page 406, there's a figure there on the left-hand side, figure 8.17. And as you can see, there is a funny-looking volume thing there. And what they did is they went ahead and, I'm not even going to try to draw this, but if you look at the PX plane, they used to cut that in, so this is parallel to the y-axis, right? And we are going to do that entire volume thing from x equals a to b. So we're taking the derivative of, the integration from a to b, and we have on each of those cross sections, you're going to have a specific cross section, right? You're going to have a cross section, and you're going to, in each slice, the thickness of that slice is going to be dx, okay? So that's how they're going to run it. So this is going to be the volume, okay? So volume is going to be the cross-sectional area times the thickness of that cross-section. So you're going to get a thin slice, and you're going to add all these slices up to make it the volume, okay? So you go to page 407, on the top there's a definition there of volume of the solid, and it looks exactly like this, okay? So let's see if we can actually try to use this onto something that we actually know how to do, all right? So let's say that I had a rectangle that looks like this, okay, and we'll call this H, and we'll call this R. And I'm going to go ahead and spin this, rotate this around the x-axis. So I'm going to end up with what? I'm going to end up with a cylinder, right? I'm going to end up with a cylinder that looks like this, right? With H and R. So what is this? This is basically a cylinder with a radius of R on the bottom, right, with a height of H. Well, we already know how to do this, right? We learned this in geometry, right? So the base area here is pi r squared, and then we multiply that by the height, and this is what the volume is what we're going to get. Okay, so we're going to derive this. We're going to get this in a different way. So what we're going to do is we're going to go ahead and cut this in slices like this, right? So where this is going to be dx, or delta x, or dx, right? So when you rotate this little strip around, okay, as we do, you're going to end up with what? You're going to end up with a thin disc. It looks like that, right? As you rotate this around, right? You're going to get a thin disc, which with a radius of r, right? When a thickness of what? The thickness is dx, right? So the volume of this thin little disc is going to be what? Pi r squared, right? Pi r squared, the area, times the height, right? Dx, right? Okay. So basically the volume is going to be pi r squared, and we're going to go dx, and we're doing this from where to where? X is going from 0 to h, 0 to h, right? 0 to h. So if I take the derivative, so I do the integral here, pi is this, these two are nothing more than constants. I get dx, there's nothing there, which means that there's a 1 there, right? So what am I going to get? I'm going to get pi r squared x, and I'm going to evaluate this from h to 0. So I get pi r squared, and this is nothing more than h, right? And there you go. That's how you derive that. It's the same thing. It came with the same answer, right? So now you know how we got this, where this equation came from. Okay? So that was kind of simple, right? Because as x goes from 0 to h, the radius actually stays the same, okay? So there's not a whole lot of, stuff going on here. So let's do something else. Let's do something, again, that we know and see if we can verify it and see how it works, right? So let's say that we had a cone instead of a cylinder this time. Okay. So let's say we had a cone. So we're going to get a cone by taking this guy here, right? We'll call this, again, we'll call this R, and we'll go from H, from 0 to H, right? If I spin this around, what do I get? I get a cone, right? I'm going to get a cone that looks like this, right? I got H and we have R, right? If I spin this around, right? So now let's look at this one, okay? So we already know, again, how to take the volume, right? The volume here is what? Volume here is pi r squared times h divided by the magic number, right? The magic number I told you was 1/3, and if you had Midnight Math too, or if you had pre-algebra with me, or even geometry, I always taught this as being the magic number 1/3, right? And we had a cone, okay? So here we go. So in this one, now I'm going to have, again, I'm going to take dx, and I'm going to rotate this around, right? Okay. The problem is now that the radius of each little slice that I cut is going to be different, right? So I have to find the equation to this line. What is the equation to this line, right? Y is equal to rise over run, like that, right? When x is equal to h, I'm going to get r. When x is equal to h, the h's cancel out. I get y is equal to r, okay? So the height of this is going to be what? Whatever x is, we're going to put x in to find the height right here, right? Not the height, I mean the radius. The radius for when I rotate this around, right? Okay. So when I get this, again, if I rotate this around, I'm going to get a disc that looks like this with a radius of, right, and a thickness of this, right? So my area of this is going to be what? R over hx squared pi, right? Because it's pi r squared, right? Pi r squared. And then I'm going to multiply that by dx, which is the thickness. And I'm going to go from 0 to h. 0 to h. Okay? And this will be my volume. Okay, so I pull the pi out. Pi 0 to h. R squared, h squared, x squared, dx. I can pull these guys out. We have pi r squared, h squared, 0 to h, x squared dx. So I'm going to take the integration here, pi r squared, h squared. I'm going to get what? X 3 to the 3rd over 3, h0. So this becomes what? This becomes pi r squared, h cubed over h squared. H's cancel out. I forgot the 1/3 there. 1/3 pi r squared h, which is what I'm supposed to get, right? So now we know where the magic number 1/3 came from. The magic number 1/3 came from when we took the integrated x squared, right? When we integrate the x squared, that's where the 1/3 comes from. So now that number, that magic number that we talked about, 1/3, you know where it comes from. Okay? All right, so that's how that works. All right? So let's go and see if we can do some questions in the book. Let's do example number 1. In example number 1, we have what do we have here? We have a pyramid. We have a pyramid that is basically 3 meters tall and it has square base on 3 meters on each side. Okay? So we're going to go ahead and we're going to try to find the volume of this pyramid. So basically what's happening is here, I'm going from here to here, and I'm going to have a pyramid that is, how do I draw this? I don't even know how to draw this 3D. So, like this, where we're going to have 3, 3, and 3. So this is 3 by 3 with a height of 3. Okay? All right. So again, as we do cross sections here, okay, so if you look at it, when the height is x, the square sides are x, okay? So we're going to get what? So for when it's x then, so when I have an x, what is my area? My area is going to be the side times the side, right? Because it's a square. And each side is going to be x, so it's going to be x squared d of x, right? And I'm going from 0 to 3, right? And there's no spinning around here, so there's no pi's or anything like that, right? So this would be the volume just like that. Right? So what do we have? So we're going to go 0 to 3, whoops. So if I take integrate that, I'm going to get one antiderivative looks like that from 0 to 3. So you get 1/3, 27, 9. Okay, so the answer is going to be 9. All right. Okay, another solid of revolution. Example number 2. Example number 2. In the region between the graph that and the x over is revolved around, okay, we're spinning this around again across the x-axis. So we're going to spin. Example number 2. We're going to spin the graph of x plus 2 plus x cosine. So it's going to looks like this, I guess. So this is between -2 and 2. Y is equal to 2 plus x cosine x. Right? So again, we're going to have we're going to spin it around like that. We're going to spin this around like that, right? So my volume is going to be equal to what? Volume is going to be equal to from -2 to 2, -2 to 2. Okay, and then so the height here, which is the radius of that disk when you spin it around, right? Is that guy here? So you're going to get 2 plus x cosine x. You take that r squared, and then you're going to have the pi, and then you're going to multiply that by the thickness, right? The thickness is going to be dx. It's going to look like that. Okay. So the book goes ahead and mints this. Let's kind of do a little bit of an exercise here. I want to see if we can go and do this algebraically. I'm not going to do all the way through, but at least I'll try to set it up for you. Okay. So let's say if we can go ahead and work on, pull the pi out, -2 to 2, 2 plus x cosine x squared dx. Okay, so this is not in the book, but let's go ahead and see if we can work this, all right? Just kind of do a kind of review how we would do this, all right? So we're going to have to do the squared first, all right? So I'm going to get what? Pi, I'm going to get pi negative 2 to 2, 4x cosine x plus x squared cosine squared x, right? So I'm just going ahead and doing the squares out right here, right? So this one's simple, right? We have no problem with this. This part, what do we have? We have to be able to do this. We have to be able to do this, correct? And how would we do this? We're going to have to say u, one is u and one is v, right? So u prime, what do we want to be the u prime? We want cosine x to be the u prime and v to be the x, so that when we do, you know what? Let me do this in a different color. U and v, so you want v to be x, you want u prime to be cosine x, which means that u is going to be equal to sine x, v prime is going to be equal to 1, right? So we're going to have what? uv prime is equal to uv minus u prime v, right? Okay? So what do we have here? I'm going to have uv, so that's going to be x sine x minus, well, this is like that, right? So we're going to have u, which is sine x, times v prime, which is 1, goes like that, x sine x, so this will be what? Minus cosine x, right? So I take the derivative of minus cosine x, I get sine, right? So sine x plus cosine x plus c, right? So that's how you do this part. How would you do this part? This part's a little tricky here. Okay, this part's a little tricky because you're going to have what? X squared cosine squared x dx, right? The problem is the squared term here, right? The squared term here, okay? So you want to make this into a non-squared term. So you would use the double angle identity in trig, and you would say this is 1 plus cosine 2x over 2 dx, right? And then you're going to get what? This would be x squared plus x squared cosine 2x over 2. So I'm going to actually pull that 2 out over here and not worry about it. Dx, right? So this guy here is simple, no worries here. This just becomes 1/3 x cubed. And then what do we have here? We actually have we can use a tabular form here, right? So it'd be x squared cosine 2x, right? And you would have to what? You want to take the derivative of this one out, right? Then over here you want to do the integration, right? So if I integrate this, what do I get? I get 1/2 sine 2x. If I integrate this, what do I get? I get cosine 2x over 4, but it's negative, right? If I do it, integrate it one more time, what do I get? I get minus sine 2x over 8, right? And then what do I do? Plus, negative, plus, right? Yeah. So I'm not going to go through the whole thing, but you see, if I asked you, forced you to do this algebraically, you should be able to do this, okay? And this is, since this is, you know, a little involved is why the book just goes ahead and nents it, okay? All right? So, and if you nent the whole thing, you're supposed to get 52.43. But I just wanted to set this up for you, right? And make sure you understand how this works, okay? So that'll be the end of part 1.